this section, we're going to take a look at what the second derivative tells us about a function. So we're going to look at the shape and the curvature of the graphs, which means we're looking at the concavity. So take a look at this first graph that looks like an upward-facing parabola. This is an example of a graph that is considered concave up. And I often will abbreviate concave up CCU. So we often say it's concave up like a cup. And this second graph is an example of a graph that is concave down, which will be abbreviated CCD, concave down. So we say it's down like a frown or up like a cup. Another way to identify concavity is to take a look at the tangent lines. So if I were to draw a bunch of lines tangent to this curve that is concave up, you'll notice that these tangent lines, although they're not particularly well drawn, they all lie below the curve. So the tangent lines lie below the curve, whereas the graph that is concave down, if you draw your tangent lines, all of your tangent lines lie above the curve. So that's another way to tell the difference between concave up pieces of a curve and concave down. But now let's take a look at what's actually happening to the derivative. So remember, the derivative is the slope of the curve. So if I were to look at the slope of my tangent lines, let's start here on the left side of this curve. Here, the slope of my tangent is negative. So here my tangent lines have a negative slope, so the first derivative is less than 0. And then here I have the horizontal tangent, that's where the derivative is equal to 0. And then my tangent lines have a positive slope, so the derivative is greater than 0. So what's happening to my derivative is that the derivative is getting bigger. We say the derivative is increasing when we have a concave up portion of the graph. The derivative will be increasing. So now if we think back to our knowledge about the first derivative test, we said when a function is increasing, its first derivative is positive. So therefore, if the first derivative is increasing, then its derivative is positive. And the derivative of the first derivative will be the second derivative. Therefore, if the first derivative is increasing, that means that the second derivative is positive. And that is a third way of telling that you have a graph or a portion of a graph that is concave up. And we call that the concavity test. So if the second derivative is positive on an interval, then that means that the original curve must have been concave up. So let's look at the concave down scenario. So again, let's take a look at the first derivative. So on the left side of the graph here, the slopes are positive, so the first derivative is greater than 0. And then we have a horizontal tangent, so we know the derivative is equal to 0. And on the far right-hand side, we have negative slopes, so the derivative is less than 0. So in this case, for the concave down graph, the derivative is decreasing because those slopes are getting smaller. So if the first derivative is decreasing, then that is telling us that the second derivative had to be negative. Remember, if a function is decreasing, then its first derivative was negative. So in this case, since it's the first derivative that's decreasing, then the derivative of the first derivative, I know that sounds confusing, the derivative of the first derivative, which is the second derivative, will be negative. So if the second derivative is less than 0, then we know that that portion of the graph is concave down. And that's often what we call the concavity test. So what happens when we have a change in concavity? That's what we consider a point of inflection, or an inflection point. So an inflection point will be a point on the curve where the graph is continuous. So a point on the curve where the graph is continuous, because we won't have a point of inflection if there's a discontinuity there. So it's a point on the curve where the graph is continuous and the function changes concavity. And the function changes concavity. So a change in concavity, either from concave up to concave down or vice versa, will be an inflection point. So think about this concavity test. If there's a change in concavity, then looking back at the second derivative, what will be happening on our second derivative? That means that the second derivative will be changing sign. So f double prime changes sign when we have a point of inflection or an inflection point. So now let's move on to what's called the second derivative test. We've previously looked at the first derivative test in another video, so now we can take a look at the second derivative test. So if we have a critical value where the first derivative is equal to 0, so that means we have a horizontal tangent, and if we know that the second derivative is positive, so that means that the graph is concave up. So think about graphing something that is concave up, and then we know we have this point here where the first derivative at that value is equal to 0, so we have a horizontal tangent. Clearly the second derivative is greater than 0, which meant that the graph was concave up, then that tells us that the graph had to have a local minimum. So f of x has a local minimum at C. Whereas if the first derivative is equal to 0, so again, that means we have a horizontal tangent, but this time the second derivative is less than 0, so that means we have a portion of the graph which is concave down. So we have a point here where the first derivative is equal to 0, so a horizontal tangent, but we know that the second derivative is less than 0, so the second derivative is negative, then that will imply that our function had to have a local maximum. So this is an alternative for finding local maxes and mins. It's an alternative to the first derivative test, where now we're looking at the sign of the second derivative to determine whether we have a local maximum or local minimum. And then the third case here is if the second derivative is equal to 0, or perhaps if the second derivative doesn't exist, then we say that the test is inconclusive, meaning we cannot use the second derivative test in these cases. So the second derivative test is only going to work when we know the sign of the second derivative is either positive or negative. If the second derivative equals 0 or doesn't exist, then we can't use this test, so we must go back and use the first derivative test in these cases. So let's take a look at an example. Let's revisit a function that we've looked at in a previous video. F of x equals 2/3 x to the third power plus 5/2 x squared minus 3x plus 6. And this time, let's use the second derivative test to determine the local maximum and minimum values for this function. So we're going to notice that the domain is all real numbers since this is a polynomial function. I always like to note the domain in case we have any discontinuities, anything weird going on. And then our first derivative will be 2/3 times the derivative of x cubed, which is 3x squared, plus 5/2 times the derivative of x squared, which is 2x, minus 3, which will simplify to 2x squared plus 5x minus 3. So then we need to go ahead and find our critical numbers. So we're going to go ahead and set our first derivative equal to 0, which will be 2x squared plus 5x minus 3 is equal to 0. And then we will factor this quadratic. Remember that if it didn't factor, we would use the quadratic formula. So 2x minus 1 times the quantity x plus 3 equals 0. So x equals 1/2 and -3. So these are the two values where the first derivative is equal to 0. Now normally for critical numbers, we would also find where the first derivative is undefined, but that's not going to be necessary. If we look back at our second derivative test, we're only looking for places where the first derivative is equal to 0. So now to utilize the second derivative test, we're going to take these critical numbers and we are going to substitute them into the second derivative and take a look at the sign of the second derivative. So if our first derivative was 2x squared plus 5x minus 3, then our second derivative is 4x plus 5. So we are going to substitute 1/2 into our second derivative. So 4 times 1/2 plus 5 will give us 2 plus 5, which is equal to 7. So now let's analyze what this means. We ended up with a positive second derivative value. So this means the graph of the function, f of x, it was concave up when x equals 1/2. So this means f of x is concave up, I'll write CCU, when x equals 1/2. So then visualize that. If a graph is going to be concave up, then did we end up with a local max or a local min? So in this case, that means we have a local minimum. However, the problem didn't just ask you to find where the local minimum occurs, it actually asks you to find the local minimum and maximum values. So remember, that means it's asking you for a y value. So now that we've determined that we have a local minimum at 1/2, then we need to go ahead and substitute 1/2 back into the original function in order to find the actual y value, the output. So now we're going back to the original. This is where you'd pause the video and grab your calculator because we want to input the original function into our calculators and go ahead and evaluate f of 1/2, which I've done and you can check me. That is going to be about 5.21. So we can say that the local minimum value is 5.21. So now we need to move on to the other critical number, which was -3. So we'll go through the same process. So let's take a look at the second derivative. So we are going to evaluate the second derivative at that critical number, -3. So 4 times -3 plus 5 is -12 plus 5, which results in a -7. So we ended up with a negative output, a negative second derivative value. So a negative second derivative means that the function was concave down. So this means f of x is concave down when x equals -3. So again, if you visualize a portion of a graph that's concave down, then that means we have reached a point which is a local max. So we can say, so we have a local maximum. And that maximum occurs when x equals -3. But once again, it's asking you for the max value. So therefore, we are going to have to go ahead and finish this off by substituting -3 back into the original function. So finding f of -3, and that works out to be exactly 19.5. So we can summarize and say we have a local max value of 19.5. So this is how we can utilize the second derivative to help us find local maximums and local minimums.